And now we want to find the power spectral density of the BFSK signal. And I have done a brief highlight of the steps required to find the power spectral density. First and foremost, we are told that this is the power spectral density. The note does not show us how we arrive at this, but what we can simply do is that we know by definition that power spectral density is symbolized by symbol S of F. So it is a spectrum of power, or where the power is concentrated in the frequency domain of a given signal. So that is what symbolizes the power spectral density. And in our last class, we said that that is normally defined by the Fourier transform of the, I think I should make this correction, is the Fourier transform of the autocorrelation function. So, and in this case, the autocorrelation function is our BFSK signal that has been generated. So this is our BFSK signal. So of course, this is the autocorrelation function. The R, normally you use R. So this is the autocorrelation function of BFSK signal. And if you remember, the BFSK signal is summarized as S, and S is a combination of S1 and S2. S of T is equals to S1 of T plus S2 of T. That is what we have. I think we have already said that, where S1 is the one that is composed of the one frequency, and S2 consists of another frequency. So that we don't have to remind you. So at this point, we are simply saying that by definition again, the autocorrelation function is defined as the mean or the expected value of the product of these two signals, except that this should be S. Just a quick correction. This should be S multiplied with S. But what we actually see in actual sense is that when you I should have plus tau. You can see this is tau and S plus tau. The autocorrelation function simply says that when you multiply a signal with itself at a different time, that gives you the the expected value. So we are going to be saying that one of them is going to be characterized by F1, and the other one is going to be characterized by F2. And therefore, when you perform this Fourier transform of this expected value, it actually shows that one is going to be a sine function that is centered at F1, and another sine function that is centered at F2. So of course there is a T there and a T there, a T. So this is how we define, we have gone through this, how to find the Fourier transform of a left function, and therefore we are able now to say that our power spectral density is defined by two sine functions that in actual sense, the one we have said that if F1 minus F2, the separation distance is actually equals to 2FB. That would now constitute this distance between the two peaks, 2FB, and we have said that you can take that one to be the case as mentioned there. But then we also know that there is an additional difference between that. Okay, there is an additional frequency that is generated by the bit rate of the incoming binary sequence, which we say that F1, this will between the center frequency of the carrier frequency and the smallest frequency that will be transmitted, there is a difference of FB. So there is one FB there, and there is another FB here. So the total of them are likely to be 4 FB. And that is, first, it gives us the bandwidth of our BFSK signal as 4FB, or that is the maximum bandwidth of our BFSK signal. At the same time, it allows us to define, this is the power spectral density of our BFSK signal that consists of two peaks, one centered at F1 and another one centered at F2. And in a similar manner, we can in a different way, without really going into the details of derivation, we can state that the power or the probability of symbol error. We can say that the probability of error of symbols that are transmitted using the BFSK. This we don't have to derive. We can just remember that is going to be given by a half of error function, the root of EB over 2 A naught, where A naught is the noise power spectral density with zero mean, and the EB is the bit signal energy.